In our previous lecture, we have seen that a magnetized material in an external magnetic field can be represented by equivalent current densities, the volume current density as well as the surface current density. Now, let us solve a numerical example so that we can build our concept. So, let us say that there is a cylindrical magnet which is uniformly magnetized. So, this is a magnetic material which is cylindrical in shape. And for the sake of easy calculations, we are assuming that the magnetization is uniform and it is in z direction. So let us say this is z direction. So magnetization is in this direction. Now x axis will be, let us say, in this direction, and y axis will be in this direction. Now you see that this magnetized material can be represented as volume current density and surface current density. So the volume current density will be del cross m is equal to del cross m naught az. Now since this is a constant, it is not varying with del or the space coordinate, so it is equal to 0. So the volume current density is equal to 0. Only the surface current density will be there, and it will be m cross an. Now for these two surfaces, the top and bottom surfaces, an is in this direction, az direction, and for this an is in minus az direction. So m cross an, m naught az cross az is equal to 0 for top, and m naught az cross minus az is equal to 0 for the bottom surface. So the top and bottom surface are not going to have any equivalent surface current density. Only the surface which is now this curved surface, it is going to have this what we can say, this surface current density. Now for this curved surface, the normal vector will be in the direction of ar, the radial vector, for in cylindrical coordinates. So the surface current density is m cross an is equal to m naught az cross ar. Now for cylindrical coordinates, z cross az cross ar is equal to a phi. So you see the surface current density is m naught a phi. Now a phi is always tangential to the curved surface. So it implies that the equivalent current density, the surface current density, is like this. It is varying along the surface, not varying, it is constant of course, but it is in this direction, curved surface direction, a phi direction. So this represents that this curved surface is carrying surface currents, and those surface currents are circulating and their direction is in a phi direction, like this. Okay, now let us take a small length dz dash, so that we do not get confused with source and the observation point. That's why I am taking prime with the source coordinates. Now let us assume that it is at z dash from the origin. Now it is given that the length of this cylinder is L. So this total length is L. And it is also given that this is having radius B. Now the surface current density is m naught a phi. So this is flowing on the surface. So per unit length it is flowing on the surface. So in a small length of dz, the current will be m naught dz. Okay. So this will be the current. Now, as you can see that on the top and bottom surface there is no current, but on the curved surface there is a current and it is equal to m naught dz, and if we just see the direction, it is in the a phi direction. Okay. Now we know, we have solved a similar numerical example that a current carrying ring with current I is going to have a magnetic field given by, on its axis az, mu naught I into b square over twice of z square plus b square power 3 by 2. This we have derived in one of our previous lectures as a numerical example, and if I multiply and divide with pi, it is simply az mu naught dipole moment over 2 pi z square plus b square 3 by 2. Okay, so this we have derived in one of our previous lectures, so this will serve as a starting point now. So for our case, the current is m naught dz dash, so dB is equal to az direction mu naught m naught dz dash, and b square will be from this quantity, I is just m naught dz dash over 2. Now in this example, previous example, this was at origin. Now here the source is not at origin, it is at z dash location from the origin, so this z will be replaced by z minus z dash square plus b square 3 by 2. So the total field will be integral of this dB over the whole surface, and as dz is varying from 0 to L, I can now clearly write it as mu naught over 2 m naught b square dz dash z minus z dash square plus b square 3 by 2. Now if I put z minus z dash is equal to b tan theta, and we can proceed from standard integral tables, or I can use this and put this here, we will find that the field on the axis at a point P, which is at 0 0 z, is simply written as B is equal to az mu naught m naught over 2, and on solving it will be z over under root z square plus b square minus z minus L z minus L square plus b square. So let us take a case when z is equal to L by 2. So in that case b will be az mu naught m naught over 2 z plus, or L by 2 plus L by 2. This will be L by 2 square plus b square under root, and this will be L by 2 square plus b square under root. So it will be az mu naught m naught L over 2 L square plus b square over this 4. So on the center, without any external field, if this magnetic material is magnetized, there will be a magnetic flux density whose direction will be along az direction itself, and its value will be given as this. So in this way, we can utilize the concept of equivalent current densities for solving the cases wherever we have magnetized material involved. So if you find that this lecture is helpful to you, then please share and subscribe our YouTube channel, and also join our Telegram group whose link is given in the description of this video. Thank you.